Today we're doing section 5.2, day 1, and it is all about estimating the area under a curve with Riemann sums, which is really what we were doing yesterday by making rectangles. These are some answers. Okay, definite integrals are Riemann sums with areas under the curve. All right. These are sums. Remember, you go from k equals 1 to some number of adding things. That's kind of the definition of a sum. We have the sum symbol, which is the Greek letter sigma. K is where to begin and end the sum. LREM, MREM, and RREM are all Riemann sums. So to find an area of the curve with the sums of rectangles, we use this little equation. And really, that's what we did yesterday. The sum of a bunch of heights times widths. The sums of areas. Okay, that's what we did yesterday. Fancy way of writing it. Now we're also going to find some other fancy ways of writing it. This means that if we, and this is the part we just saw, areas length times the width, which is length times width right here. This is the sum of all those rectangles that we had. And what this says is if we take a limit and make those rectangles very, very, very small, with the subintervals being very small, so many that you can't even draw them, that is where we get closer and closer to the exact amount of the area under the curve. All right, for more information on that, look in your book and read section 5.2, just so that you get all the details of that. All right, now we're going to write this sum notation as an integral notation. That's what the integral means. Take the area under the curve from the point A to the point B, this is your function, times the interval. And this dx interval is a small, small, small interval, the change in x, so that we can make as many, it's actually a limit, so we can make as many little rectangles as possible. Here's the definition of all the parts of the integral sign. All right, and this is called the integral. It's cute. It's like a long S. I'm sure you've seen it. All right, so first thing we're going to do is make these sums into integrals. So we're going to use the integral sign. We're going to use our endpoints of integration from 0 to 10. All we're doing is rewriting this sum into an integral. So we go from 0 to 10. Our function is x to the third. With a c, we're going to change to an x dx. That is your answer. All right, don't be freaked out by how crazy this sum looks. Really, that's just your answer. Rewriting the sums of rectangles as an integral. Here's one more example like this. This time we're going from -3 to 4. And here is our function, c of x, which just means, or ck, which means an x, and sine of x, dx. Okay, that's it. Let's not make it harder than it is. Okay, the next one. Here we're actually going to look at the integral of a constant. And really this is like our train problem we did at the very beginning of section 5.1, where we had a function. This is our function c. And we had our function c, which is just a constant function. We wanted to find the area under the curve between 2 and 5. And we found that if we multiplied the difference here, 3, which is b minus a, b, a, and this is your c, that we found that we could take 150 times 3 and get your answer. All right, so the way we write this out with an integral using the numbers, this is 2 to 5, our interval of our problem, times 150 is our constant. This means that we take 150 times b minus a. Right, that's what we're doing here. And that's just 150 times 3, which is 450. Okay, so that's what we do with a constant as our integral. Okay, integral of a constant. We'll do a lot more with that, you'll see. Okay, in order to do the next few problems, because we are going to take areas under the curve and calculate using geometry, these are 3 equations you should know: circle, triangle, trapezoid, area. Know them? All right, so we are going to calculate integrals using the area under the curve, because that is what this means. The integral sign means the area of the curve between 1/2 and 3/2. This is the lower level of integration down here and the upper level up here. All right, and then our function is negative 2x plus 4. So this line is negative 2x plus 4. That's the line, negative 2x plus 4. It has a negative 2 slope, and it, I think this intersects right here too, but it doesn't really matter. And it intersects the y-axis at 4. So we want to find the area under the curve from here to here. So this is what we're looking for. This is called a trapezoid, and therefore we're going to use the trapezoid formula to calculate. All right, the height of this is actually the width between 1/2 and 3/2, and that is a 1. Okay, so that's going to be our H number. Our base is one of the heights right here, and the other base is the other height at 3/2. So those two are the function at 1/2 plus that little function at 3/2. So we need to see what value those have. And that's going to be our area under the curve. So here's another way to calculate area under the curve. Besides using rectangles, adding up all the rectangles, you can actually calculate. If you have a figure that you can calculate, like a triangle, trapezoid, rectangle, circle, you can calculate it using geometry. Okay, 1/2 times 1. What is that function at 1/2? I think it's 3. Okay, plug 1/2 in there, you get 3. Plug 3/2 in here, and you're going to get a 1. So do that math, and you get the area under the curve is 2. Okay, the next example is similar, except we may have a different figure. This function is r, so f of x equals r, which means it's a straight line going up like we have drawn here. We're going from the lower level of integration to the upper level of integration. So again, the area under this curve is another trapezoid. Trapezoids, okay. So, area equals 1/2 h b1 plus b2. Okay, so the first, and the base is really our height. It's really height, or base times height 1, height 2. But, okay, so this is going to be, the height of this is going to be b1, and the height of this is going to be b2. Now, this function happens to be a line, so this is square root of 2. And over here, this is 5 square roots of 2, right? So that's our b1 and b2, square root of 2, 5 square roots of 2. And here we need to take 5 of these minus 1 of these. I think we get 4 square roots of 2 in between there, so that's our height. 1/2, 4 square roots of 2. And here we have a square root of 2 plus 5 of them. And we need to do this math. We have 4 square roots of 2 times 6 square roots of 2 times 1/2. The area then is 24. Okay, check my math on that, but I'm pretty sure it's good. All right, calculate the integrals using the area under the curve from the interval -2 to +2. If you draw this function, you get 1/2 of a circle. The area of 1/2 of a circle is 1/2 pi r squared. Okay, as I see it, this half circle has a radius of 2. So we're just going to plug that in. Notice how this can be a lot simpler than making a bunch of rectangles. So if you can find a geometric figure to calculate the area under the curve, do it. So this is 2 pi, I believe, and that's our answer. Okay, thank you for playing. It's a cute little thing. Thank you for playing 5.2 day 1. And we are done. A 10-minute video. You're going to love it.